Hello, Mr. Sok Satyarith, Anratana, Kuratana, David, and Mr. David, can you hear me?
Yes, sir.
How is the quality of my voice? Is it clear enough?
Not clear at the moment.
Not clear, really?
Now it's clear, sir.
It's clear, right? Okay. Okay, Mr. Chishtai. David Ratana. If it is not clear, let me know immediately. Okay, I'll just check. And my internet connection is good. I'm just using only earphone. So, guys, I hope you're all doing well. And we are here again. And hopefully, I will meet you in campus next Tuesday, I guess, because I have just heard that they got permission to continue our studies at the campus. Okay, and after that we will decide, okay, what days we are going to meet in the campus, what days we are going to have our classes online. So in the last week, right, it's our second week, I guess, we talk about functions of several variables, especially functions of two variables and functions of three variables. And all types of functions of multivariables, they are based on these two things: functions of a single variable, two variables, and three variables. If you really grasp the idea of these three functions well, you can understand other, let's say, multivariable functions pretty well. And after all, we are just using the same properties to deal with any problems involving multivariable functions. And also last class, we talked about limits and continuity in higher dimensions, how to calculate the limit of a function of two or actually two variables, right? And also how to prove that the limit of a function does not exist. To do this one also, if you remember, we had to just show at least two different paths, which actually shows us that along this path, when we approach to a certain point, right, the value of the function approaches two different values, which means that the function does not have a limit at that point. Because for a function to have a limit, regardless of any path, right, when you just get closer and closer to a certain point, also the value of the function must get closer and closer to a single point. Otherwise, it doesn't make sense, because that's the definition of a limit. So today we are going to talk about partial derivatives. Okay, partial derivatives, actually it is derivative. Why we are saying partial derivative? Because we are dealing with a function of multivariables, function maybe two variables, three variables, four variables. That's why it's called partial derivatives. So the calculus of several variables is similar to single variable calculus applied to several variables at a time. Now, as we just give the definition, you will see that actually the definitions and the properties, a lot of things, not everything, but most of the things, it is very, very similar. But the only difference here is that you have to keep in mind that we are dealing with the function of several variables, and only in your functions we are involving more variables. But when we're differentiating this, actually, for example, let's say if you're given a function of two variables, x and y, what do we mean by differentiating a function with respect to x or y? So if you're going to differentiate it with respect to x, that means that we are just going to hold y a constant. Okay, you're just treating y as a constant. And if you remember this, we did a similar thing in implicit differentiation, right? If you're given an expression, for example, let's say in xy, let's say x squared plus y squared is equal to, let's say, 0. And differentiating with respect to x or y, it is the same thing. Because if you're differentiating that thing with respect to x, then you are treating y maybe as a function of x or as a constant with respect to x. Anyway, so what we have here, some key concepts in this section: partial derivatives of a function of two variables, calculations, that means how do we calculate the partial derivative of a function, functions of more than two variables, partial derivatives and continuity, second order partial derivatives, the mixed derivative theorem, and partial derivatives of still higher order, and the differentiability. Okay, these are the key concepts in this section of this chapter. We are going to have some idea or knowledge about these concepts. Okay, now guys, let's start with this definition. So the partial derivative of f of xy. So now we are first starting with defining the partial derivative of a function of two variables. And as you know that the graph of the function of two variables, right, is a kind of surface. So immediately we can just imagine any kind of surface. For example, what is it? Let's say the pumpkin, for example, because pumpkin inside is empty. That's why it's a kind of surface, right? So maybe pumpkin, or what is it? Maybe watermelon, or a piece of cheese, or a piece of meat. Okay, of course, maybe inside is empty. It is something like this. For example, just for simple example, suppose we are given a kind of watermelon, right? So watermelon, two different ways you can cut this. That is, let's say if you just put this on the table, and after we introduce our x-axis and y-axis, right, we can just cut perpendicular to the x-axis or perpendicular to the y-axis. Okay, so see in this picture, we are given this a part of the graph of this function because its graph is a surface. So now, how do you define the partial derivative of f with respect to x at the point x sub 0, y sub 0? Okay, so it is defined as we are just using del, because that del means that's actually, of course, the same thing is also derivative, but we use del that emphasizes that we are dealing with a function of multivariables, maybe two variables or three variables, to emphasize the difference. Actually, still the same thing, it's a derivative. So partial derivative of f with respect to x at point x sub 0, y sub 0 is defined as the limit as h approaches 0. Here we are given an increment to x sub 0 because now we are holding this y sub 0 as a constant. What does it mean? It means that y sub 0 constant means that we are cutting the graph of this function that is perpendicular to, what is it? Here we have x, right? Here we have y, right? It's perpendicular to y-axis. You see here this red line, okay, it's a kind of plane that passes through this red line. And at the time, you see here, if you just cut this, if you're looking from the front side of, what is it, this graph, you will see a kind of curve. That's blue is a curve, right? Here, at this point, y is constant. What is changing here? X is changing here, right? You see here, x is changing, but y does not change at a single point. So we are given increment to x-axis here, x sub 0 plus h, and y sub 0 is constant, minus f of x sub 0, y sub 0 over h, provided that the limit exists. So if this limit exists, then we are defining this limit. What is it? A partial derivative of f with respect to x at x sub 0, y sub 0. So what is it actually? Simply, if you're given a function, for example, let's say, if you're given a function f that is x and y. Let's say our function is 2x squared y plus xy squared plus 3, for example. So by this definition, then what is the derivative of this function at, for example, let's say with respect to x, okay? So this means that actually just treat this y as a constant function. The constant, okay, the constant number. So y is a constant number. At the time, how do I differentiate this? So just differentiate with respect to x. 2x squared, right? So that's equal to 4 and x and y plus, and y squared is a constant number for us with respect to x, and derivative of x is equal to just y, 1. So here we have y squared. And the derivative of 3, that's equal to 0. So this is the derivative of this function with respect to x. So now next thing is if you are asked to calculate its value at a certain point. For example, let's say, what is the derivative of this function with respect to x at, for example, let's say it is 2 and negative 1. So that's equal to 4 times 2 times y negative 1 plus, here we have negative 1 squared, which is equal to negative 8 plus 1, that's equal to negative 7. So that means that at this point, if you draw a tangent line, okay, because it's surface, by tangent line, the slope of this tangent line is negative 7. All right. So the partial derivative of y with respect to y actually also defined in a similar way, but this time now, if you are going to differentiate a function of two variables with respect to y. So that means that now we are treating x as a constant, which means that we are cutting, right, the graph of the function with the plane that is perpendicular to the x-axis, at which actually goes through the x-axis at x sub 0. Right, see here again, this red line. Red line is a kind of plane. We are just cutting this through this plane. Okay, so see here, if you just look again from the front side of this curve or the surface, you will see a curve. So at that point, you draw a tangent. This red line is a tangent, and the graph of the function is y, because here x is constant. Again, the derivative means we know it's a slope, right? Or the slope of the tangent line at this point. So again, similar way, the partial derivative of f with respect to f of xy with respect to y at the point x sub 0, y sub 0 is, what is it? Partial derivative of y with respect to y. And here at this point, x sub 0, y sub 0 is defined as the limit. It's a special limit as h approaches 0. Here we have f of x sub 0, y sub 0 plus h minus f of x sub 0, y sub 0 over h. So here we are given increment to y-axis, because this means this, right? Because we know that the derivative of the function means that instantaneous rate of change of the function at a point, right? If you just change a little bit that the value of y, what is the change in the value of the function? That gives us the idea about the derivative of the function at the point. Anyway, these are the simple definitions. Now, again, we'll see more examples. Before we move to the example, let's talk about notations. And some different ways you can use these notations to represent the partial derivative of the function. The first one is d dx. It looks like ordinary function, but here we have f of x, y sub 0, because y sub 0 is constant here, right? And here we have x equals x sub 0. That means that here we are differentiating this function with respect to x, evaluating its value at x equals x sub 0. Y sub 0 is always already positive here. Or we are using this del notation, del f, which means that partial derivative of x with respect to, partial derivative of f with respect to x at x sub 0, y sub 0. Right? It's also in a notation. Of course, they mean the same thing depending on the context. We can just use these notations interchangeably. And the third one is f in subscript notation. We can just use small x, which means that we are differentiating this f with respect to x at x sub 0, y sub 0. Or del z del x, and here we have vertical line in subscript notation. Here we have x sub 0, y sub 0. That means that we are differentiating function z. Z is a function of, what is it, x and y with respect to x at this point. And some more compact notations, we can also use fx or del f del x or zx or del z del x. They all mean the same thing. They all mean the same, what is it? The quantity, which means that it is the derivative of the function f with respect to x. Askara, how are you?
I'm fine, sir.
Are you in Phnom Penh now?
I'm in Sihanoukville, my hometown.
Really? Will you come
Yes.
to the university next Tuesday?
Sure, I will go. It depends on my health. I was sick in the last 2 weeks, and I'm not feeling good right now. So
Feeling good? What do you mean? You have high temperature or just sick?
yes, sick like the flu.
Ah, flu. Okay. But you may not feeling well, but don't tell this anybody, okay? People may panic.
Yes, sir.
Yeah, I know these days people are very sensitive, right? Even if you just sneeze, they worry about you, or even if you have flu or high temperature. Yeah, anyway, I hope actually you will get well soon, and I will see you in the campus in the shortest time possible. Okay, guys, good to hear from you, Askara. Let's continue. Now let's say a few examples about calculations. Find the value of del f del x. That means that partial derivative of f with respect to x, and also partial derivative of f with respect to y at the point 4 minus 5. Okay, after actually having these definitions, let's just practice a few examples, and later you will see the applications. And really, if you understood the single variable functions, how to differentiate well, these derivatives are not so hard. Okay, so easy. because usually differentiation is much easier comparing to integration. Okay, integration is a little bit challenging, but still I'm sure that you can handle this by just practicing a few questions. And of course, you should sit and think what's going on here. Okay, what's going on here? Try to visualize. And also in this way, you can improve your thinking and the visualization skills. So, okay, now let's focus on this example. Here, we need to calculate, what is this solution? Number one, del f del x, right? We have to differentiate with respect to x. So partial derivative of f with respect to x, that's equal to the first one is differentiate x squared with respect to x, that's equal to 2x, plus differentiate 3x constant, that's equal to just 3y. In respect to x, y minus 1 is constant, that's why it's equal to 0. So now if we evaluate the value at the given point, del f and del x at, what is it, 4 minus 5. That's equal to 2 times 4 plus 3 times negative 5, which is equal to 8 minus 8, that's equal to 0. No? 8 plus minus 15 is equal to minus 7. And how about the second part? The second part is we have to differentiate this with respect to y. But usually these two partial derivatives, usually they are not equal to each other, because drawing a tangent, okay, one is in two different directions, they give us different slopes. Anyway, here we have, what is it again, differentiate this function with respect to y, x squared with respect to y, it is constant, that's why it's equal to 0. And how about if you differentiate 3xy with respect to y, that's equal to 3x, and y with respect to y is equal to 1, and negative 1 is equal to 0. So partial derivative of f with respect to y at the given point, what is it? It is 4 and minus 5. That's equal to 3 times 4 plus 1, that's equal to 13. Okay. So this is how we calculate partial derivatives. Next question, another example. Find partial derivative of f with respect to y as a function if f of xy equals y times sine of xy. Because we are not calculating this as at a single point, right? At any point. So that means that also the result will be another function. So here our function is f. Let me just write here fxy is equal to y times sine of xy. So with respect to y, let me just use this notation fy, right? So first, it's just the product of two functions, right? Here, y times sine of xy. Again, just apply the property. What is it? If you differentiate the product of two functions, first we have to differentiate the first function times the second function plus first function times the derivative of the second function. So now if we differentiate y with respect to y, it is 1. So here we have 1 times sine of xy. Plus here we have y times, now we have to differentiate sine of xy with respect to y. So if you differentiate sine of xy with respect to y, first we have to differentiate it as argument, right? This xy that's equal to y. Times, after that we have to differentiate sine with respect to xy. So that is cosine of xy. So which is equal to, now if you simplify this, that's equal to sine of xy plus y squared times cosine of xy. Okay. Another example, calculations. Find partial derivative of f with respect to x and partial derivative of y with respect to y as a function, or as functions, or as a function. Should be as here, as a function. If f of xy equals 2y over y plus cosine of x. Okay. The solution. First, if we differentiate this again with respect to x, right? So here in the numerator, we don't have x. It's just like, what is it with respect to x? It's something like this. Here we have k1 over k2 plus f of x. It's something like that because with respect to x, y is constant here. So now if you differentiate with respect to x here, that's equal to what we have here. Let me just write here 2y times y plus cosine of x to the power of -1, right? So we have to differentiate this. Okay, first let me just write it as f. Okay, that is our f. So now how do we differentiate this? So fx is equal to, here we have 2y just constant, right? First -1 comes to the front. Now here we have y plus cosine of x to the power of -1, that's equal to -2 times. Now we have to differentiate the expression inside the parentheses, right? So here we have y plus cosine of x. If you differentiate with respect to x, the derivative of y is equal to 0. Derivative of cosine of x is equal to minus sine of x. So which is equal to minus is plus. So that's equal to 2y times sine of x over, here we have y plus cosine of x squared. So that's the derivative of this function with respect to x. Let me just write here, I need more space. I better write this 2y times sine of x over y plus cosine of x squared. Okay, that's the first part. How are the second parts? Let me just use different color here. So now we had to differentiate this with respect to y. Okay, it's just, what is it? With respect to y, we have the quotient of two functions, that is f1 over f2. And also from single variable, calculus, you know how to differentiate this, right? U over v prime equals u prime times v minus u times v prime over v squared, the same thing. So here, if you differentiate with respect to y here, because cosine of x is just, what is it? Constant number for us with respect to y. So here we have y, fy, that's equal to, first, if you differentiate 2y with respect to y, it is 2. 2 times y plus cosine of x minus, now here we have 2y times, differentiate the denominator with respect to y, that's equal to just 1 over, right? So that's equal to y plus cosine of x squared. So that's equal to, if you simplify this, 2y, they cancel each other. So that's equal to 2 times cosine of x over y plus cosine of x squared. Okay, that's it. Another thing, example 4, find del z del x if the equation defines z as a function of the two independent variables x and y and the partial derivatives exists. Okay, actually here for example 11, we can just use the idea of implicit differentiation, right? Because here the function itself is involved in the expression yz minus natural z. But if you try to express the z explicitly in terms of x and y, it will be more complicated. So just keep in mind that actually z is a function of x and y. So at the time, if you differentiate both sides with respect to z, what am I going to do here is, so here we have del and del x. Here we have y z minus natural logarithm of z equals del x. Here we have x plus y. That is very, very important. What is it? Operation in math, right? Especially solving equations, because if you apply the same operations to both sides of the equation, of course, considering some special cases, if there is, it does not actually change the solution of the equation. But also here, it does not change the nature of the function. That means that it just produces another equivalent expression or function. So, or equation, let's say here, if you differentiate y times z, we have the product of two things, right? And the y, first we have to differentiate y with respect to x, that's equal to 0, right? And the differentiate z with respect to x, so here we have y times zx minus, how about natural logarithm of z? If we differentiate with respect to x, right? So here we have z prime, that is zx, because you're talking about partial derivative. In the denominator, we have just z. On the right-hand side, derivative of x with respect to x, that's equal to 1, and y is equal to 0. And that's it. So on the left-hand side, actually zx is a common factor. Zx, just factor out this and express this as a single fraction. So here we have y times z minus 1 over, here we have z. On the right-hand side, we have 1. So now from here, dot, partial derivative of z with respect to x will be equal to, just take this fraction to the right-hand side, that's equal to z over y z minus 1. And of course, also we have implicit function here because z is a function itself, and the expression itself involves our function. Okay. So let's do one more question. After that, we will have break. Okay. The plane x equals 1 intersects the paraboloids z equals x squared plus y squared in a parabola. Find the slope of the tangent to the parabola at 1, 2, 5. So that means that if you're cutting this with a plane, because x equals 1, it's not a line in three-dimensional space, right? It is a plane. If you just cut this, what is it, paraboloid, or paraboloid with this plane, and what do you see if you look at this from the front side, you see a parabola, right? X equals 1. And also you can understand this, since it is here, it's the same thing as you are dealing with this. Z is equal to, when x equals 1, it is 1 plus y squared. So now we are considering this in this plane. Here we have, and this one is y, and this one is x, sorry, z, right? And 1 plus z squared, what is it? It's a graph, is something like this. This parabola. So this point is, it is, yes, it is 1, right? When x, y equals 0, it is 1. The question here is, we have to find it is derivative at 2, 5. What is 2, 5? Here we have, let's say this p, that is 2, 5. Okay, it's the same thing. So at the time, the partial derivative of z with respect to y. Actually, here z equals x squared plus y squared with respect to x squared is 0. So that's equal to 2y. So it says find the slope of the tangent to the parabola, right? We have to find the tangent. So tangent is equal to, let me just label the tangent by m. So that m is equal to del z over del y at, what is it? At 1 and 2, which is equal to 2 times 2, that's equal to 4. So the slope of the tangent to the parabola at the given point 1 to 5 is 4. Okay, guys, that's it for this session. Let's have some break. Okay, maybe 15 minutes. After that, we will continue and talk about the rest. Okay, see you after 15 minutes. A break.